Our next speaker is Moses Na from the MIT. He's a graduate student from the Mechanical Engineering Department, entering his third year as a graduate student. And he will start his presentation now.
Thank you for the presentation. Thank you for the introduction. I'll share the slide. I assume everyone is seeing the full screen, is that right? Awesome. Okay, hello everyone around the world. My name is Moses. I'm from MIT. I'm a third-year graduate student under the McKee department. And today I will talk about my research, which is shown in the title as Manipulating a Whip, the Advantages of Primitive Actions. This is the brief agenda of today's presentation, 12 minutes for the main and 3 minutes for the Q&A session. And without further ado, I'll dive into the presentation. Tool use is the hallmark of human behavior, and we are just extraordinarily good at it. In the field, there are a plethora of examples which demonstrates this fact. You can see from this video, which shows the remarkable dexterity of humans, and you can see we are just so good at it, right? This person is not even seeing the object being diced, and look at the speed of it. So we are just really good at it. Inspired by this distinct feature, there are intensive research going on in the field of human tool manipulation to eventually transfer this remarkable dexterity onto robotic system. But still, we don't exactly know how and why humans have become such master tool users. Well, people might just say we have much better hardware and software, and that might be the main reason, right? However, the paradox is humans perform so well despite their agonizingly slow neuromuscular system. The neurotransmission speed is a million times slower than mechatronic systems. The bandwidth of our muscle actuators are much lower than electromagnetic and electrohydraulic actuators, which are often used in the robotic systems. We have large feedback loop delays, which profoundly impairs real-time reactive control. Our system is extremely slow, but we end up with this performance. So how is this possible? Well, this brings up the internal model hypothesis. Rather than achieving motor skills based on real-time supervision or intervention from the central nervous system, slow neuromuscular system implies that prediction based on some form of internal model may play a prominent role in human motor control. Although prediction based on some form of internal model plays a prominent role in human motor control, the exact nature of the model itself still remains to be clarified. And within these lines of researches, which aims to elucidate the nature of the internal model, we have the so-called dynamic motor primitives hypothesis, claiming that humans achieve their remarkable dexterity by composing movements based on at least 3 distinct classes of motor primitives, which is submovements, oscillations, and mechanical impedances. In detail, submovements for discrete point-to-point movements, oscillations for rhythmic repetitive movements, and mechanical impedances, which manages the physical interaction with the environment. So we believe or contend that the remarkable dexterity of humans, despite the limitations of the neuromuscular system, is achieved by composing movements based on these 3 motor primitives. To test this working hypothesis, we study one of the most complex and exotic tools which humans can manipulate, which is a whip. And why specifically a whip? Well, some people might suggest an internal model based on a detailed mathematical physics style form, but thinking about the daunting complexity of the tools we are able to manipulate, this seems implausible. And the great example for this is a whip. A whip is an extremely complex object. First, it is flexible, which means it is an extremely high degrees of freedom structure, in principle, an infinite number. It has complex and challenging dynamic behavior. For instance, the wave equation of the whip requires nonlinear partial differential equation of infinite order, where the numerical complexity taxes even modern computational resources. The complexity of the mathematical physics style model is almost unmanageable, which profoundly limits any optimization-based approaches. But almost ignorant about this daunting complexity, humans are able to manipulate it almost without any apparent difficulties. So what this observation implies is that rather than an internal representation based on a detailed mathematical physics style form, we claim that humans simplify motor tasks based on primitive actions. And thanks to its daunting complexity, WIP is a perfect subject to test our working dynamic motor parameters hypothesis. So enough for the introduction, the main contents of the research. We studied in simulation whether a distant target could be reached with the WIP by using a controller composed of dynamic motor parameters. Quantitatively, the goal was to minimize the distance between the tip of the WIP and the target. All of this study was done in the Mujoko simulator, which is the acronym of multi-joint dynamics and contact. The model used for the study was a 54 degrees of freedom model, 4 degrees of freedom for the upper limb and 50 degrees of freedom for the WIP. In detail for the upper limb model, 3 degrees of freedom at the shoulder and 1 degree of freedom at the elbow. And torque actuators were mounted coaxially on all 4 joints. Everything distal to the wrist was excluded from this model. The continuous dynamics of the WIP was modeled as a discrete lumped parameter model, which consists of a serially connected mass spring and damper system. 25 of the submodels, which individually consisted of 2 degrees of freedom, were serially connected in a chain-like manner, which results in a 50 degrees of freedom system. The values of the WIP parameters, for instance, the mass, spring, damper coefficients, were measured and derived from the actual bull WIP. And finally, the upper limb and the WIP were connected with the freely rotating 2 degrees of freedom universal joint. The controller of the upper limb model was composed of dynamic motor parameters. It used the first order impedance controller with gravity compensation. In detail, the K and B matrices are the stiffness and damping matrices of the upper limb, which corresponds to mechanical impedances of the dynamic motor parameters. And the Q0 or Q0 term, which is the zero torque trajectory or the reference trajectory, was composed of a single discrete upper limb movement, which corresponds to the submovements of the dynamic motor parameters. In detail, the zero torque trajectory Q0 was used as the input reference trajectory of the upper limb model. In other words, the input of the controller was the Q0 trajectory. A bit of a side note, but essential detail, the zero torque trajectory Q0 is some sort of reference trajectory or posture of the upper limb model. So based on the first order impedance controller equation, the postural deviation between the zero torque trajectory Q0 and the actual trajectory Q evokes torque on each joint of the 4 degrees of freedom upper limb model. And this torque eventually generates the upper limb movement. You can see from this animation that to propel forward the upper limb, the zero torque trajectory, which is shown in red dashed line, precedes the actual upper limb, which is shown in blue. And at the end, the zero torque posture kind of pulls back the upper limb to slow it down to end at some specific posture. Summarizing, the upper limb controller used the first order impedance controller with the feed forward Q0 term, which is the input of the upper limb controller. Note that by composing the movements based on dynamic motor parameters, the upper limb movement was generated by defining the 9 movement parameters of the zero torque trajectory, which is the initial posture, final posture, and the duration it took from start to end. Based on the design model and controller of the upper limb, the WIP targeting task was defined or framed in some sort of optimization process. The goal was to find the optimal 9 movement parameters which could reach the distant target with the WIP. 3 targets were tested for this, one just in front of us, the 2 which was 45 degrees tilted on the left, and target 3, which was 45 degrees elevation added onto target 2 position. We conducted 600 iterations for the optimization. The optimization algorithm first defines the 9 movement parameters, which consist the zero torque trajectory, fires that out to Mujoko, and fetches the minimum distance between the tip of the WIP and the target. And based on this value, it adjusts the 9 movement parameters throughout the 600 iterations. So we ran through the optimization for each target for 600 times. And these were the results. So within the 600 iterations, regardless of the target position, the optimization converged to the optimal 9 movement parameters. These are the optimal movements which were generated from the Mujoko simulator. And in detail for target 1, which is just in front of us, you can see from the graph that although there's a lot going on in the graph, like you can see that the zero torque trajectory, which is shown in the transparent dashed line, kind of precedes the upper limb to drags forward. And it ends out that specific posture. target 2, which is tilted 45 degrees on the left with respect to target 1. And target 3, which you need to sort of overcome gravity to reach the distant target. So note that by composing the upper limb controller with dynamic motor primitives, the control of a 54 degrees of freedom system was dramatically simplified to search in the 9 movement parameters of the zero torque trajectory, which could reach the distant target. And based on this approach, by framing the controller with dynamic motor primitives, any detailed mathematical physics-style form of the whip was not required. So regardless of the mathematical complexity or dimensionality of the object being manipulated, the control task was completely summarized to search in the 9 movement parameters, which minimize the distance between the tip of the whip and the target. So the conclusions. The takeaway of this is that by using the approach of dynamic motor primitives, it was able to dramatically simplify the control task of an extremely high degrees of freedom system, which was, for our case, 54 degrees of freedom. And it was able to identify the optimal 9 movement parameters, which could reach the distant target. And to the extent that this dynamic motor primitives approach offers a simplified solution to flexible object manipulation, this approach may also facilitate robotic control system for flexible object manipulation, which is currently a major challenge in the robotic community. And that's it for my presentation. This was funded by this kind of information. You can see from the presentation. And thank you.
Okay, thank you. It's a really nice presentation. We have now time for some questions. The audience can ask them in the chat. Maybe I start with one. Do you have any plan to take this to a robotic, real robotic arm or something?
Yeah, exactly. Although it's kind of postponed because of this virus, but yeah, we're definitely looking forward to implementing this to the robotic system, actual robotic system.
Okay. Do you have the robotic system already, and you will use the algorithm, or do you still have to develop all the robotic part?
Oh, we have a Baxter in our lab, so maybe we'll try implement this algorithm to that. So.
Okay. So I think we have no questions right now. Nevertheless, I think it was a really great presentation, and maybe we can move to our last speaker of the session.